Good morning, good afternoon, and good evening, everyone. Welcome again to the RTDS Technologies User Spotlight series. This is week number 3, and we have some more great user presentations with the RTDS simulator to share with you today. My name is Katie Sidwell, and I am a simulation specialist on the sales and marketing team at RTDS Technologies, and I will be your host and moderator for these events. If you have already been joining us, these housekeeping notes will be a bit of review for you, but there are a couple new things to say today, so I just want to cover that before we get started with our exciting presentations. First, I want to let you know that all throughout the presentation, we encourage you to submit your questions via the Q&A widget. You can just type your question in, and we will be answering those questions all throughout the presentations today. And then after both presentations are complete, we will do a little verbal Q&A and discussion as well. We also encourage everyone to say hello in the chat widget. Feel free to introduce yourself and your company and where you're from if you wish. It's really nice to see some familiar names and meet some new folks. Not quite as good as seeing faces, but we will have to save that for a future event. I also wanted to mention a little something about the video quality. We've noticed that this webinar platform has reduced the quality of our slide videos a little bit, so it may be difficult to read some of the very small print in some of the graphs and figures. In this case, we encourage you to take a look at the actual slide files, and they are available to you in the Handouts widget. So if you can't see the Handouts widget, you can go to your icon menu at the bottom and click the icon that looks like the pieces of paper. And this will open up an area where you can access the slides for both presentations. And these are really high quality, so if you're curious about a particular diagram, you can absolutely access those that way. The recording, both the video and audio and the slides, will be made available to you right after this presentation. So the access for the on-demand content gets emailed out to you once we're finished today, so you can check it out after the fact as well. Finally, we do have some extra time in today's session. Our user presentations were a little bit shorter, so I'm going to take 5 to 10 minutes at the end of the session after the presentations are complete and go through some of our newer or updated sample cases in the RSCAD software. And if you have any questions about those sample cases as I go through them, please feel free to submit those in the Q&A as well. Now, without further ado, let's get to our first presenter. Franz Stadtmueller received his BS in Electrical Engineering, Power Systems, and Electronics from the University of Wisconsin-Madison. He works as a senior advising electrical engineer in the Grid Technology, Engineering, and Evaluation Unit at Pacific Gas and Electric's Applied Technology Services Department. Prior to PG&E, he worked at SPX Transformer Solutions in extra high voltage testing. Franz is a subject matter expert in the area of power system modeling and electrical testing, and has most recently been the ATS technical lead on PG&E's Rapid Earth Fault Current Limiter, REFCL, project, Smart Meter Partial Voltage Detection, and Remote Grid and Grid Needs Assessment, SIME Python automation projects. He has also supported United States Department of Energy projects under the Sunshot Initiative, modeling and studying distributed PV generation and electric vehicle integration. Please welcome Franz Stadtmueller, who will be presenting Compensated Distribution Networks for Reducing Wildfire Risk in California.
Thank you and welcome everyone. Talking today about some new technology for California to reduce our wildfire risk, as you probably have seen in the news the last few years, and especially this year with some lightning caused wildfires. But we're looking at ways to reduce the wildfire risk from electric infrastructure. So I've worked for Pacific Gas and Electric, a little bit about the company. It's in Northern California with a service area of over 70,000 square miles. So we have a very large service area. 16 million Californians are served through PG&E infrastructure. We have 22,000 employees who live and work in the communities we serve. And we have a lot of solar connected facilities on our circuits as well, 340,000 solar rooftops connected. So the project I'm talking about today is part of the Electric Program Investment Charge, which is a California statewide program that allows utilities like PG&E to invest in and pursue new or novel emerging energy solutions to meet California's energy goals and drive innovation. So this EPIC program promotes building the energy network of tomorrow through innovations focused on increased safety, which is the primary focus of this project, improved affordability, and greater reliability. And the EPIC program has a lot of value to both PG&E and the state of California. It enables us to fulfill our mission to safely and reliably deliver affordable and clean energy to our customers and communities every single day while building the network of tomorrow and invest in a sustainable energy future and reduce greenhouse gas emissions while also driving affordability and maximizing value for our customers. So specifically, this project is known as EPIC 3.15, proactive wires down mitigation. So when a ground fault occurs, such as a power line breaking and hitting the ground, it can create a spark, potentially starting a fire. So this project was initiated to reduce the risk of a wires down scenario and prevent a fire ignition. So resonant grounding can be used to reduce this fault current. And it's also known as compensated electric distribution network. So I'll refer to these two interchangeably. And specifically, we're looking at a technology known as Rapid Earth Fault Current Limiter Technology, or REFCL, or REFCL. So I'll be referring to this as REFCL through this presentation. This technology is an extension of resonant grounding, and it's installed at a distribution substation to neutralize the ground fault current and prevent a spark in the first place. So a fault will still occur, but the REFCL will prevent that from sparking and igniting a fire. And this technology has been successfully deployed in Australia to reduce the risk of fire from ground faults there. And one specific type of REFCL is known as a ground fault neutralizer, or GFN, and this is the specific type of equipment we're installing as part of this project. And I know we have people from all over the world participating in this Spotlight series. So here in the US, we refer to Earth as ground, but it's referred to as Earth in other parts of the world. But we're referring to the same thing here. So in the US, we typically use direct or solid grounding for our power systems. This results in thousands of amps of fault current if you have a ground fault or a wires down situation. So we're just showing that ground current path at remote Earth back to the source and through the lines. And then with resonant grounding with REFCL, the fault current is reduced to less than 0.5 amps of fault current. It does that by compensating the fault current. So we'll go into more detail about that. But we show the same path here, so the sum of the fault current at the fault site is very small. So how does REFCL reduce the current so drastically? How does it work? It uses active compensation. So as I mentioned, it's an extension of resonant grounding or a traditional Peterson coil, which has been around for 100 years now or so. But during a fault, an inverter actually increases the neutral voltage to reduce the faulted phase voltage to 0. So in this diagram here, you see our system normal on a 12 kV system. Everything's balanced. And then when a fault occurs, the REFCL actually increases the neutral voltage in phase with the faulted phase, so that the phase to ground voltage of the faulted phase gets very small, close to 0, and thereby reduces the fault current. So the arc suppression coil and the inverter both work together to reduce the fault current to almost 0 amps, substantially less than half an amp. So we started this project with a proof of concept since this is new to the US. So we built a control hardware in the loop or chill simulation using the RTDS. So we modeled the ground fault neutralizer on one of our substations and the connected distribution circuits. And we're looking to determine the fault sensitivity considerations. So to have the highest sensitivity, there's a lot of other things that need to happen on the circuits in preparation for this deployment. And also develop and test the control hardware through automation. So we're looking to run a lot of different scenarios and verify the performance of the control hardware, that it's doing the right things, making the right decisions. And lastly, determine the optimal settings to inform our field commissioning. So we're hoping to have some settings already verified, and we can hit the ground running, so to speak, with the field commissioning. So we had to build the RSCAD model from scratch. So our distribution circuits are typically studied in SIMDist software, and RTDS offers a conversion tool. So we use that to convert 2 circuits with nearly 160 miles of total distribution circuit miles into RSCAD. We previously did field phase identification for all the lines on these 2 circuits. So we had the phase identification loaded into our SIMDist software. And first we reduced the model as much as we could to simplify the study and reduce the size of it. And then we used the SIM to RSCAD conversion utility to bring that into RSCAD and then build on the model from there. So this, like I said, we modeled the real Calistoga substation. It's located in Napa Valley, California. So it consists of a 3-winding Y grounded delta bank, 66 kV to 12 kV. The secondary connection changes, of course, with resonant grounding. So we isolate the bank's neutral from the ground, and we can switch it back to solidly grounding if we want with a switch. And then we included the detailed model of the ground fault neutralizer, which 3 main components are the arc suppression coil, which is a reactor, the tuning capacitors to adjust between resonance, and then also simulated the inverter, which is a voltage source connected to the secondary winding of the arc suppression coil. And this is a photo of what these pieces of equipment look like, with the ASC on the left, the inverter in the middle, and then the controls equipment on the right side. Once we had everything imported and built out, we had to make some tweaks to the model. So we simplified it further to make it easier to do the studies, and we're really just focusing on major parts of each circuit. So we established equivalent series and shunt impedances using Thevenin equivalence. We studied voltage regulators and their effect on the neutral voltage. And we included the major protective devices with DMP3 communication for the control hardware in the loop. So we've got the feeder circuit breakers included and the automatic circuit reclosers tied to our central control hardware. And our circuits we have some load current unbalance, so we also wanted to model about 10% unbalance on the load currents as well. So then we built the actual control hardware test bed, which consists of a number of different devices. So the first is the neutral manager controller. So this is what makes decisions on detecting a fault and then locating what circuit the fault is on, and working with our central controller, which is known as a Station Earth Fault Management Relay, or SEFM. So we'll keep the acronyms going. So this is serves multiple purposes, but it's an interface adapter for the neutral manager controllers for a SCADA system. So it's DMP3 based, and then it also gives us another layer of control flexibility. So we can do custom logic and custom control schemes with this CEFM device that aren't built into the neutral manager controller. So we can really customize our implementation. Then we wired up 2 power amplifiers to the simulation. So these are providing the voltage and current inputs to the neutral manager controller. And then we also interfaced to the RTDS the digital inputs and outputs cards. And we use the analog output card to drive the reference to the power amplifiers. So then I built a user interface in the RSCAD runtime, and we're still adding more to this interface. But this is what it looks like currently. So we can look at the load on the bank, look at the voltages, and observe how the voltages change when a fault occurs and once it's being compensated. The nice part with this system as well is when there's a fault, we don't need to immediately interrupt service to the customers. Since the fault current is so low, it buys time to locate where the fault is and try to isolate the fault while keeping the rest of the customers online. So we see that through monitoring the loading on the bank. And then we have the phasor diagrams for the phase voltages and also the neutral voltage. So we can see the neutral voltage shift during a fault. We also have the arc suppression coil tuning. So we have full visibility onto what position is in, and depending on which circuit reclosers are closed in or not, it'll affect the tuning of the ASC. So it'll automatically tune to resonance if there's a change in topology of the circuits. And then right now we're just manually controlling the fault control, but we're adding more automation to go through the automated scenarios. So here's an example simulation result. So we created a fault on one phase, a ground fault, and observed the control response. So the first thing to point out is there's no immediate service interruption. And we see through the fault trends that the fault current starts out very small. So the arc suppression coil is compensating most of the fault current. But then the inverter kicks in and drives that current to be very small. As you can see, it's close to zero amps. And then we see the neutral voltage increase as this process is finalized. So this was a fault on A phase, and the voltage has dropped to basically zero, very close to it. And we see the full neutral voltage shift on the other phasor diagram. And once the fault is identified, the neutral controller identifies and locates which circuit the fault is on. And from there, our CEFM controller applies the circuit tripping to first trip the reclosers and lastly trip the feeder circuit breaker if needed to isolate the fault. So one of the big advantages of this technology is its sensitivity to ground faults. It's much higher than other methods of handling the neutral in a power system. So we're simulating and detecting very high impedance faults. There's some side effects that reduce the ground fault sensitivity though, so those must be addressed to increase it to be as great as possible. So since we have unequal lengths of each phase conductor out in the field, that results in unbalanced phase to ground capacitive currents. And so that causes a standing neutral current at the substation bank and in turn a standing neutral voltage. So if that's too high, then that reduces your sensitivity. So the solution to this is to actively balance the capacitance with a new piece of equipment called a capacitive balancing unit, where we can control the amount of current per phase we're injecting into the ground. And with this, we should be able to reduce the standing neutral current at the substation to 100 milliamps or less, ideally. And this would allow for detection of fault impedance greater than 16 kilo ohms on a 12 kV network. So we want to make sure that we're able to detect a half amp of fault current to begin with. And in addition, single phase voltage regulators, which operate independently and have their own controller, reduce sensitivity. So with a closed delta voltage regulator, if they're tapping on different taps, it shifts the neutral and causes imbalance. So the solution is to use a multi-phase voltage regulator controller with group tapping so that all the phases tap up and down together. And so the tap position target is calculated based on the average voltage of all the three phases. And this allows us to maintain balance at the substation despite changes in load and the voltage regulators regulating voltage as they should. So a little bit more about the automation. So we're using RSCAD scripts to automate the simulated fault testing so we can perform hundreds of scenarios and verify the control functions. And we're also looking to calculate the fault energy based on the initial transient of the fault and the steady state current. So we're using a target of 0.1 for the I²T value. And this was derived from ignition tests performed in the state of Victoria in Australia. And based on this value limit, it gives a 90% risk reduction for ignition. And then we're also looking to use the variable resistor component so that we can change the fault impedance without having to restart the simulation. It's just a more efficient way to do the testing, and so RTDS has supported us on making this component available. And we're currently in the process of finalizing this automation piece. So if anyone has any other suggestions for this, definitely would encourage you to speak up in the Q&A later. Face some challenges with the RTDS simulation for this project. So it's electric distribution application. RTDS is typically used more for transmission studies. So our starting circuit model from our SIMDIST software is very detailed with thousands of nodes. So we had to simplify it down. We had to look at what really matters for our analysis. And so we decided to really just look at each circuit recloser zone and then calculate the series and shunt Thevenin equivalence for each recloser zone. So that simplified things a lot and made it a lot easier to run the simulation and build upon it. And then we did multiple iterations to tweak it some more and verify that the results lined up with our SIMDIST software. But we still left RSCAD running in distribution mode for this application. We're doing a 200 microsecond time step, and that's adequate for the studies we're performing. And the inverter used in the GFN has a proprietary serial communication protocol. So we're in the process of simulating the inverter and its current injection a little bit better. So we're looking to convert this proprietary protocol to Modbus or maybe some other support protocol to communicate with the GTNet X2 card. So we're making some progress there. And then lastly, we did our simulation so far with the GFN connected directly to the bank neutral, but it's actually connected through a grounding transformer. So we're in the process of finalizing this model so that it's 100% in line with the field installation. So further work in this area, the initial results look promising. The proof of concept that we've done so far did just that. And so the field installation is currently in progress. We're developing and tweaking our automated circuit recloser tripping algorithm, which will use DMP3 protocol. And like I said, since we're limiting the fault current to close to 0, it buys time to use a standard control protocol like DMP3. We don't need a real high speed one, such as Goose or something like that. And then we're looking to determine the maximum reliable ground fault sensitivity. So we want to make the system as reliable as possible and drive the risk of ignition down as much as we can. And then we're finalizing the controller settings. So we've already made some tweaks there for detection thresholds, and that'll help us when it comes time to do the field commissioning later this year. And lastly, we're going to validate the simulation results with actual field testing. So we're in the process of building a test rig with high voltage resistors so that we can go out into the field and do a test without tripping any circuits. We can verify the performance of the REFCL in the substation, and we can compare those waveforms with the waveforms in the simulation and tweak the simulation even more. And with that, I'll invite any questions, and thank you for your time.
Thank you, Franz, for a great presentation. We've gotten some great questions so far. Reminder to everyone to continue submitting your Q&A, and we will be responding online throughout the next presentation and then discussing afterward. Our next presenter is Abdul Azeem Mohammad from Dubai Electricity and Water Authority, or DEWA. Abdul Azeem Mohammad, MSEE, has been working as an RTDS specialist at Dubai Electricity and Water Authority since 2014. He received his B.Tech degree from Jawaharlal Nehru Technological University, India, an MS degree in electrical engineering from Polytechnic Institute of New York University, Brooklyn. After his graduation, he worked for Corporate R&D, Power Systems Division at Siemens Corporate Research Center, and later worked at Nyack Corporation Incorporated. He has provided trainings and worked on consulting projects using both PSCAD and RTDS. As an RTDS specialist at DEWA, he was responsible for setting up RTDS simulation laboratory for testing protection relays. His current responsibilities include standardization of RTDS testing procedures for DEWA protection applications, testing and analyzing suitability of relays from various manufacturers across the world specific to DEWA requirements. Please welcome Abdul Azeem Mohammad, who will be presenting use of the real-time digital simulator in Transmission Protection Department at Dubai Electricity and Water Authority.
Thank you for the introduction, Katie. Hello everyone. Hello RTDS world. Thank you RTDS Technologies for organizing the User Spotlight series. I'm sure all the presentations will be helpful to the users one way or the other, and I'm very much looking forward for all the presentations. Before we begin, I would like to thank my management at Dubai Electricity and Water Authority, Transmission Protection Department for giving me this opportunity to present the RTDS lab setup at DEWA. Our topic for today's presentation is use of real-time digital simulator and Transmission Protection Department at DEWA. In this topic, we will cover the following. Number 1 is the challenges in DEWA power system. Number 2 is use of RTDS at TPD for protection relay testing, followed by the hardware and the amplifier capacities, need for high current ratings, uniqueness of amplifier setup at DEWA, process of testing and standardization, and finally our future plans with the laboratory here at DEWA RTDS TPD. When we say Dubai, the first picture or thought that comes to our mind is glitzy, flashy streets, tall buildings, and a lot of energy. Yes, it's a fast-growing city with exceptional performance in everything it achieves, all thanks to the wise leadership and their vision. Every stakeholder contributes to keeping up this vision, and DEWA plays an important role. I'm sure it is on the bucket list for everyone to visit. Now, coming to the network at DEWA, it is a very tightly knit network with close proximity of source and load, contributing to short lines and addition of vital equipment like reactors, capacitor banks, SVCs, etc. All this because of strategic location nature of the city. All these factors contribute to very high short circuit currents in the network. Other factors include rapid expansion of the city, thereby contributing to increasing load, environment and weather conditions, where the summer peaks reach 50 degrees centigrade coupled with sandstorms. Challenges due to renewable energy integration with projects like world's largest solar power project, rooftop solar integration, we call it Shams Dubai, EV charging stations, automation and digitization of pretty much all the services, to name a few. Owing to all the above factors, it is very critical and important to maintain the reliability and efficiency of the system, and network protection plays quite an important role. Use of RTDS at DEWA TPD. RTDS laboratory at DEWA TPD is an important advancement in relay testing and approval process. With the help of RTDS laboratory, protection relays that are coming in to be approved for use in DEWA network are tested thoroughly and specifically to DEWA network, which would otherwise be tested by manufacturers on a generic network with lower short circuit currents. All existing relays in the system can also be tested to evaluate their performance and take corrective actions, if any. The laboratory also helps to test and simulate the scenarios that are not identified and simulated by open loop test using test kits. But having said that, in our experience, sometimes these kits have their own advantage in troubleshooting. The simulator exposes a relay to real life and extreme conditions. It helps analyze the system response in all these stages, that is pre, during and post fault conditions. Ability of the test setup to retrieve the disturbance records helps in identifying the underlying issues with relays as well as the settings. Above all, it helps in establishing a manageable and affordable in-house simulation and testing facility. The RTDS hardware capacity at DEWA comprises of 6 racks of RTDS with 24 PB5 cards, a range of IOs with quite a high number, a GTFPI as well, and the GTNet cards with all the protocols and a GT-Sync card. The amplifier channel capacity at DEWA comprises of 9 channels of 25 amps, 42 channels of 32 amps current, and 3 channels of 250 volts as voltage amplification and 28 channels of 300 volts. The RTDS laboratory here at DEWA is equipped with 7 CMS356 amplifiers, 1 CMA 156 and 1 CMS 156 amplifier. The 7 CMS 356 amplifiers are the latest generation of amplifiers offered by Omicron with higher current capacities. They also offer the flexibility for number of channels, individually catering to low currents and when combined for higher current rating outputs. We will come to the uniqueness of the amplifier setup in coming slides. The laboratory is also equipped with Arbiter 1088B GPS clock, environment monitoring system to monitor and maintain real-time temperature and humidity of the test environment, high current connectors and test leads that were specifically designed and tested to ensure minimum voltage drop between the amplifiers and equipment under test. This is the setup we have at the DEWA TPD RTDS laboratory. To the extreme right is the amplifier setup, where we have 7 CMS356 amplifiers mounted in a rack. The 5 amplifiers in the first rack provide about 150 amps RMS for 1 second, and the bottom plate in each of those cubicles is for the high current outputs. Then we have our 6 racks of RTDS as well as the RSCAD to run the whole setup. Now, uniqueness of DEWA RTDS amplifier setup. As mentioned in my previous slides, the short circuit current is very high in DEWA network, and when we test relays specific to DEWA network to evaluate the complete performance of the relay, we expose the relay to same short circuit current experienced by the relay in the field. The amplifier setup at DEWA RTDS laboratory can generate currents from 25 amps RMS to 150 amps RMS when in parallel without any drop for relay burden with up to 0.1 VA. The amplifiers were rigorously tested for the following and passed all tests satisfactorily with a maximum error of less than 1%. They are steady state AC amplitude test for various current ratings all the way from the individual channel of 25 amps to 150 amps RMS. Same for the transient AC response under multiple configurations to cater to all the scenarios or all the protection applications at DEWA. Burst short test was done to analyze the amplifier output deviation under continuous operation and temperature rise. Then comes the propagation delay, if any, step response, and presence of second harmonic. Here the idea is to show what happens when the current injected in the relay is more than the A to D current limit. Some relays clip the current with the A to D converters, some relays have their internal CTs saturated. The fault with high short circuit currents coupled with extreme scenarios like remnants could affect the relay performance or stability. This high current injection with extreme scenarios can be done in a safe, secure, and virtual environment to understand the behavior of the relay under these extreme conditions. Here are some of the current levels in DEWA protection applications. You can see for 400 kV bus reactor, it's about 140 amps secondary, and 132 kV, it's about 133 amps, and also chopping limits of one of the manufacturer. DEWA RTDS laboratory over the period has enhanced the workflow with standardized DEWA protection application, test report formats, and testing requirements to deliver optimal testing with minimal time. Moving forward, DEWA RTDS laboratory will continue testing of existing relays to evaluate their performance and also test new relays as part of their relay approval process. We are also getting ready to provide RTDS testing facility in the region for utilities customers with high current amplification requirement, and also to enhance the capacity and capability on protocol-based testing for protection relays. That concludes pretty much what I have to present. Thank you everyone for your attention. I am joined by my DEWA TPD protection expert to take your questions if any. Thank you.
Thank you very much, Abdul, for the great presentation. Just prior to discussing the Q&A that you've all sent in, as promised, I'm going to take a few minutes and just go through some of the sample cases that are available in our RSCAD software. So I've pulled up RSCAD here. You may or may not be very familiar with this software. I am running our most recent version, RSCAD 5.011. And this is our file manager. So here's where I can launch all of my modules and also access all of my user case files. So I have my personal files here, and then I can also open this tutorial folder, which has a read-only folder with our samples directory in it. So these are all cases that are available that we've created. Many of them are documented. So I'll begin by opening our distribution mode folder. Franz was mentioning distribution mode in his presentation. It's something that they have used at PG&E. And here we have a few different cases that were developed in distribution mode. One of them is a SIME to RSCAD sample case. And this case demonstrates how the IEEE 123 bus case can be converted from the SIME software to RSCAD. So that might be interesting to some users. I want to show you our new updated IEEE 123 bus case, because we have added a hardware in the loop testing component to this case. So this case has 4 voltage regulators in it, as you may know if you're familiar with the case. And the new thing we've done is update the first voltage regulator so that the control is provided not by internal controls components to RSCAD, but by an external voltage regulator controller. So here you can see the interface components, which are the basis of our hardware in the loop interface with the external regulator control. And I can open up my case documentation here. We have a new section for interfacing the voltage regulator. So you can see here we're using an SEL AVR controller, the SEL2431. And we're using an amplifier to provide secondary level voltages and currents to that voltage regulator controller. Something interesting that this case includes is a tutorial on how to set the scaling factors for the analog outputs and how to set up the amplifier to complete this interface. So that's something that Abdul was talking about in his presentation quite a bit. The secondary side values that we're providing to the controller here are 120 VRMS and 0.2 amps. So in order to provide that, we need to amplify our signals coming out of the RTDS's analog output card. So this chapter explains how we have chosen our amplifier settings and also how we've set the gains internally in the RTDS, which is what we call scaling. So this case might be interesting to users that want to get more familiar with our distribution mode library and also to incorporate a hardware in the loop aspect to their testing. Next, I will bring your attention to the main step folder, our electric vehicle sample cases. We updated our EV model so that it provides bidirectional power flow support. Both charging and discharging are now supported. So this is a slightly larger EV sample case. You can see there are a variety of RL components representing shorter lines, dynamic load components, these EV charging stations, and we have our actual EV models. The EV and charging station models work together. So the charging station is essentially a controlled load that draws P and Q from the grid, and then the EV requests its power from the station. There are 2 ways to control the reactive power for the EV charger. There's direct Q control by the user, and then there's the ability to use the reactive power for voltage control. And you can see that the source of that reference signal can come directly from the user in runtime or using a control word within RSCAD. Each EV can be connected to up to 10 different charging stations. I'll open up the EV here. The V2G, or vehicle to grid control, can be automatic or manual. The auto control allows the user to set the state of charge limits, and charging will start or stop based on that. And the manual control allows the user to adjust dynamically using a slider in runtime or via a control signal. Moving on now to some energy storage cases. So I'll transition into the substep folder of our samples directory. In addition to our battery samples case, we now have flywheel and pumped storage systems examples. And these sample cases are fully documented. I'll open the flywheel as an example. So the flywheel is basically modeled as an additional mass on the rotor of our PMSM, permanent magnet synchronous machine model. So here we have our multi-mass model, and we're calculating the state of energy for the flywheel turbine. And then we have our converter that's interfacing the flywheel with the grid. And this whole case is simulated in the sub-step environment at a relatively small simulation time step. Here we can see our back-to-back two-level converter, our grid side and our motor side converters, and our firing pulse generators. And then we have our machine model here. And our grid side controls, and our motor side controls. Last but not least, I will show our fuse case. It's under the protection automation section of the main step. This is a newer case which is aimed at demonstrating protection coordination between various devices in a distribution feeder. And there's a focus on branch fuses. So the idea is to reduce the blowing of fuses for temporary faults. And to do so, we're simulating a feeder relay and recloser, which are configured to have a two-shot reclosing cycle, where the initial trip and two reclosing attempts are set to be based on instantaneous overcurrent elements. And the operation will then switch to a slower time overcurrent element to allow the fuses to blow. And we can demonstrate that fuse saving activity with this case. So here we have a source representing our larger power system, our distribution transformer stepping down to a 13 kV distribution feeder, and we are serving these three dynamic loads. And here we have our branch fuse models. Back in my controls hierarchy boxes, I have my fault control logic. There are various places on this system that I can throw a fault. I have my circuit breaker controls. And I have my various protection functions for my feeder relay and my recloser. I'm going to go ahead and compile this case. And I'll open the runtime interface, the operator's console. I will run the case to give a quick demo in real time. I'm working from home, so I am accessing some RTDS simulator hardware at our headquarters via my computer's VPN. Now the case is running and I can see various values updating in real time. Values like the breaker current here are displayed using meters, and once I initiate an event, we will see my plots update. So here I have my fault control. I have an A phase to ground fault selected. My fault duration is 400 milliseconds. And my fault location is bus 4, which is here where fuse number 2 sits. So I'll go ahead and apply my fault. And I can see my system's response. So we can see that the recloser's instantaneous overcurrent element has detected that fault and initially tripped the breaker. And then it sends its first reclose command back to the breaker, but the fault is still persisting, so the breaker closes back onto the fault, causing that instantaneous overcurrent element again to issue its second trip signal. Then we have the second reclose issue, and that reclose is successful as the fault has cleared. You can also see at the second reclose attempt that the instantaneous element has been disabled and the feeder protection has been switched to the time overcurrent element. So the coordination of the protection in this way has prevented fuse 2 from blowing in this case of a temporary fault. That is all we have time for today. So I would like to start the question and answer period. All right, thank you everyone for all the great questions you've submitted today. Hopefully we haven't had any audio or video issues and you can hear me clearly. I'm going to go ahead and kick it off with a question that we had for Franz regarding the SIME conversion tool. So the question is, what were some of the challenges that you faced using the SIME conversion tool, and what verifications were performed to ensure model fidelity? So if you wanted to maybe comment on a bit of the validation that you did, and if you want to touch on some of the node limits that you were coming across in the RTDS too, that would be great.
Sure. I just unmuted myself, so hopefully you can hear me. Yeah, so distribution networks have much higher node counts than, say, transmission systems. So between these two circuits, we're in the thousands of nodes. So we had to reduce it down before we brought it into the conversion tool. So we did that by really simplifying it down to the circuit recloser zones. So we did equivalent circuit calculations and just made the modifications in the SIME software first, and then we brought it in and did the conversion, and we worked closely with the RTDS team as well to handle some series equivalent impedances and things like that, so we could do reduction just in the conversion tool itself. So I was able to excuse me, simplify some things further automatically. And then after that, we did some fault studies with the system solidly grounded to compare with the SIME software and make sure that the fault duties were close, so that we knew that the series impedances were captured appropriately. And then we added the shunt impedance afterward, so we did some calculations outside of the SIME software to come up with the equivalent shunt impedance, and so we added that to each recloser zone and move forward with the simulation. Great question.
Excellent. Thank you very much. I think that's pretty interesting to our users in terms of how utilities are doing that sort of work. Another question regarding the speed of the technology that you're presenting on today. How fast is this technology in terms of reduction of voltage? And related to that, a note on motivation. Was the motivation here that your traditional protection wasn't fast enough? Or if you could just expand a little bit on motivation, that would be great.
Sure. So here in California, the drought has resulted in really severe fire-prone conditions. So we wanted to look at ways to improve our fault sensitivity. So even a tree resting against a power line coming in contact can start a fire here. So the protection system needs to be able to detect this type of fault and mitigate it. So our traditional solidly grounded system isn't sensitive enough to that. So by going with a resonant grounded system and extending on that, we can detect high impedance faults, such as a tree resting against a power line, or as soon as that power line breaks and hits the ground, the system will detect it and start actively compensating the fault current. As far as the speed of it, it depends on the fault impedance. So I'll focus on low impedance faults to give you an idea, but based on the simulations and testing observed in Australia, if you have a 400 ohm ground fault, which is low impedance, the system responds in less than 100 milliseconds. So it's very fast. It's limiting that I²T value to less than 0.1. So it's very little energy that's going into the fault site, and that's how the ignition is prevented.
Great, thank you very much. We have a question here for Abdul or Owen, so hopefully we can get them on the line here. You mentioned that the transmission lines, many of them are short in the DEWA system. And the question is regarding challenges related to that in modeling. So if there's a necessity to model these as traveling wave models for the sake of the protection testing, Was there an issue with that in the RTDS at all? Because there is the minimum transmission line length for modeling it as a traveling wave model.
Hi, yeah, this is Azeem, and yeah, regarding modeling the transmission lines, and so yeah, they're very short lines. So most of them are right now underground cables. So we are using them as cable models. But in places where we had to model the transmission lines, we were selecting more lines which were more than 15-kilometer long lines in order to standardize the testing. But in cases where we are having challenges, yes, we are going to the frequency dependent models.
Okay, great, thank you. And I wonder, Abdul or Owen, if you want to expand a little bit on the type of protection schemes that that you are testing, like which type of elements you're testing at DEWA. Okay, I think we might be having some audio issues there. So I will come in with a question for Franz, and if Abdul or Owen are able to answer afterward, that will work as well. Franz, we have a question. Is it not possible to offset the neutral current to the current that's normally there during normal operation, rather than using that capacitive current injection to drive the current to zero? So why does that current need to be reduced through the balancing method?
Right. So if we were to use the inverter or the RCC to compensate that standing neutral current to try to balance the bank, we'd actually be increasing the voltage on the neutral. So the neutral voltage is used to detect the fault in the first place. So with everything balanced through the capacitive balancing units, the standing neutral voltage is less than 50 volts primary, so it's very small. So if we have any you know any high impedance faults on the system, that neutral voltage will increase above a set threshold, and will detect the fault, and then the system will actively compensate for it. So yeah, we can't use the inverter to balance, unfortunately, because of the neutral voltage increased side effect.
Great, thank you. Abdul or Owen, I don't know if we're getting audio from you, but if you want to discuss a little more details about the type of protection schemes you're testing, and maybe whether you're planning on involving IEC 61850, for example, in the future, please feel free.
Yes, we have standardized all our protection applications as part of our standardization process. So all the protection applications are pretty much tested based on the standard models, and considering the worst possible CTs in the system and the worst possible network areas. Coming to 61850, yes, we do plan in future to do the testing on 61850 as well. And as mentioned in my presentation, we are equipped with GTNet cards to do the testing.
Excellent, thank you. I think we are running out of time here, so I will give one last question to Franz. We have a question about single versus three-pole operation. So currently are your fuses single-pole operated? And what do you think about the effect of three-pole operation on the protection systems? Will it be helpful to this REFCL technology?
Sure. Yes, most of our fuses are single pole operated. So if with standard protection and solidly grounded, if there's a ground fault, the fuse will blow and clear the fault. With REFCL, the ground fault current is so low that the fuses won't operate for ground faults, but they'll operate for phase-to-phase faults. So that's important, because if we have a phase-to-phase fault on a long tap line, two fuses would blow and clear the fault, but you'd still have the third line connected and energized. So that would introduce unbalance and if it's high enough unbalance, then it can cause false operation of the REFCL. So we've done a study of the system and determined that certain locations we need 3-pole tripping. So our reclosers are 3-pole tripping or gang tripping, and we've actually converted some of these fuses to a fuse saver product where they're individual devices, but they communicate to a central controller right on the pole, and they do the 3-pole tripping that way. And from a protection standpoint, 3-pole tripping is preferred for protection because it prevents reverse or backfed faults from occurring, especially if there's a wire down scenario. So it's our preference.
Excellent, thank you. That's a very interesting new technology to be learning about. And we certainly had a good amount of questions about it. I want to remind everyone too, if you are going to watch this presentation on demand afterward, or if a colleague of yours is going to watch it on demand, you just log into this platform and you can access it again. And you can submit Q&A after the fact, and it will be submitted to the presenters via email. So if you want to be involved in the conversation on an ongoing basis, that is one way to do that. With that, I think we are out of time. So I just want to thank all of our presenters, Franz, Abdul, and Owen, for being with us today. And I hope that we will see everyone next week in our week 4 presentations.
Thank you very much.